right, we're live. We're live. I know some people didn't want to see us, but I don't want to ruin my streak, even though it's 1 a.m. Hey, it's October 19th somewhere. So, anywho, let's get into it. Yeah, y'all thought I was done. We ain't done. We ain't losing our streak here. So, what are the goals for today? I first want to create a GitHub repo to put all my notes. I think that'd be super useful. So we're gonna do that first. Yeah. All right. Man, I'm tired, so I'm probably not gonna. This is probably gonna last an hour. We'll probably just go with the minimum, which is an hour. We're new here. I try to do at least 1 hour a day on this project. But if I don't get there, I don't get there. No, you know what? No, we'll get 1 hour. Hmm. Hmm. Mm. I already have one. Sick. I already have my repo. Call it Q Shield. So let me just connect my good notes. Actually, let's just go ahead and ask chat for what it thinks. Let's just ask chat. Um, how should I upload good notes to GitHub? I don't know, there are a lot of ways to do it, but I want to get a fast way. Initialize Git. What? Okay, this is kind of extra. Oh yeah, so this is kind of standard. So I'm gonna get a command prompt. We'll set Git. Mm, honestly, that's too much work. I'm probably just gonna upload. Let's check my good notes. Oh wait, it should be saved in the Google Drive. It should be. Oh, right here. Oh, there we go. Man. Oh, good notes in my drive. There we go. Okay, bet. Let's get. Wait, where's my notes? Oh, I think this is it. Is this it? This is it. Is it updated? I think it is. 28 pages. Yeah, it's updated. Holy crap. How do I? Can I open it in Google Docs maybe? Will it fuck up the formatting? It's a real question. If it fucks up the formatting, I might just change it. Is there an easy way to like do this? I have no idea how I can. Oh man, I don't want that. So I want to just have like one big doc. Oh yeah, NASA fucked up everything. Okay, that's what I thought. But I want to keep track of everything. I guess we'll just. Cause I want to put it in GitHub. That's the thing. I want to put this into GitHub. It says. No, I don't want this though. Is there a way that I can just let's go back to the GitHub. I want to see if there's an easy way to add file, upload file, maybe. Fuck. I think it's harder than I thought. It's not easy. It should be, but I guess it can't be easy. Mm-mm. 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 No. Mm. We'll draw. Okay, sure. Good notes files. Yeah, sure. Let's make this public. I'm okay with that. How do I? How do I get anybody can view? How do I get anybody can view? This is really weird. Get link. No, wait. What? Organize? Oh, share. Here we go. Copy link. Manage access. Anyone with link can view. Yeah, I'm cool with that. All right. Put it. We can put it in the README. That's probably smart. Say top phone notes. Can I? Cool. Say now anybody who wants. So she has to be able to see it now. If you want to see these notes for yourself, you can modify them, do whatever you want, throw them away, download them. I don't care. Everything about this project will be open source. Full notes are here, and you can see. Okay, wonderful. Okay, so the notes are here. We'll keep a note page open. Let me close this. Yeah, I'm really procrastinating my comp work stuff right now, but I don't care. This is worth it. Okay, so let's see where we left off. So yesterday we talked about, if I'm not mistaken, we looked at an application of the closest vector problem. Just gonna open up everything here. That's right, we had an actual application. We figured out what a bad basis and a good basis is. So, um, good. Let's first recap what we did. So how does myself and you guys can see it too. Okay, so the video we watched yesterday went over the shortest vector problem. No, sorry, closest vector problem. It's pretty cool. Hmm, sorry. The problem was like this. I'm gonna summarize. Let's take this to be our lattice. Okay, so this the columns form lattice, right? So the whole point we talked about yesterday was we're trying to take a point. So let's say, use a different color here. Let's say, let's consider the point. The point we used yesterday was 11.6, 4.2. Now, this point, let's call this point P. It does not exist in L. right? And that's a pretty easy proof. We know that because this is an integer lattice. There's no possible way we can get this. So we have to approximate. So we approximate. And the way we go about this, so the trivial way we went about this was we just set up a matrix. So let's call this method one. And it was easy. You set up a matrix, take lattice. Here's our basis vectors, multiply through a sum point, and will equal, oh, whoops, and will equal, I'll just abbreviate for now. I think that's better. We'll abbreviate with P. So we need to find, we need to find these 2 points. And we can see here, this is a pretty easy problem. We just consider the inverse of this lattice. This is basic linear algebra. You take the inverse of this lattice, and then you times it by P. And if you were to work this out, you can plug this into a calculator. What do we get? That's right. We got 13.4 negative 22.9. Okay, so cool. So now we have an approximation. Is the approximation right or not? We have no idea, but we have an approximation. And this is the easy way to go about finding an approximation. So what we're going to do, so whenever we look at this, we'll tell you what is the approximate value of this. You're most likely going to round to the nearest value, meaning you're going to round maybe something like 13 negative 23. That's a very common rounding, right? You just round to the nearest. But there's a problem with this. So the problem, we're going to actually draw. We're going to draw. Oh my gosh, that is horrible. Can I? Okay. There we go. We're going to draw a brief picture that kind of looks over this lattice. So let's take this. This lattice is an R2. So let's say, let's take each of these basis vectors and let's plot them. So basis vector 1 will go 6 and 14. This is right here. We'll call this B1. That'll look something like this, right? Then we have 3 and 8 is our second vector. Let's make this 3, 8. So 3, comma 8 will look something like this. Let's call this the second basis vector. We'll go through there, right? Because the basis vector must include the origin. So the problem is, the point we're trying to find here is 11.6, comma 2. So if we draw this out, I'm going to use black. 11.6, comma 2 is probably like 4.2 is probably right here, right? This is P. The problem is, with given our approximation, we pretty much said, so the problem with this, to draw this out, I'll abbreviate and say this is a big problem, right? We don't want this. And the problem with this is that if you plug this back into the original equation to find this approximation of P, right? So now we're just going to do this, right? So what should this result be? This result should be P, or it should be very, very close to P. Because this right here is, so because this is the exact value, but we can't put, if you notice, oh, whoops. If you notice, I'll make a little note here. You can't put the exact value of this into this because this is an integer lattice. Meaning you have to take, so to keep this as a lattice, this has to be an integer vector. So that's why we have to round, right? This is what the whole point of this problem. But the problem is here, if you multiply this out, what you end up getting, I wrote this down here. Oh, wait a minute, wait a minute, wait a minute. Let me get one calculator out really fast. Okay, you know what? No, I just have a calculator on here. What am I doing? There's a calculator right here. So what this is 6 times 13 plus 3 times negative. Where's the negative sign? Let's count. There we go. There we go. Sorry, I was right. The first value we see here is 9. Let's go ahead and write that down. 9. What is our second value? If you'd work this out, I'll let you do the math. This is going to be negative 2. Cool beans. Do you guys see what the problem is? Oh, whoops. Whoops. Hang on. Hang on. Sorry about that. We don't care. We care about this tab. Okay. Problem with this, if you were to plot this point, let's call this point P2, you really ended up like closer to here, right? P2. The problem is this is a really big gap, right? You're not even close to this. And for this lattice, I mean, there are many different points that you could get that are close to here. If you would imagine a lattice looks something like this is really a pretty bad answer, right? So just undo all this. And I can't even undo it. Okay, that's really annoying. So yeah, the problem is that's a really bad answer. What do we do? What's the solution? The solution is, so I'll make this note as number 2. You pick a good basis for this lattice, which you don't know what the good basis is. Like, you need a good lattice reduction algorithm. This is the whole point of the problem. This is why it's an NP-hard problem. And if you notice, this will span the same lattice as this. Now you're probably asking, well, how does it span the same lattice? That's a great question. There's no easy way to tell. The only way you can tell if two lattices are the same, which we talked about, was if they share the same unimodular matrix. So in this case, we'd have to compute 3, 0, 0, 2 equals, I won't do the math here, but I'm just showing you how to do it because I did this yesterday, times some unimodular matrix. So I'll make a note. This is unimodular, meaning that +1 or -1. I worked this out. This matrix is actually 2174. It's pretty cool. And you work this out, determinant equals 1. So yeah, that's just a pretty cool proof, but that's not really important to what we're doing here. I thought it would be just cool to mention, so we can just, I guess, there has to be an easy way to erase stuff, man, because this is just crazy. There has to be an easy way to erase this stuff, man. This is ridiculous. They make it so hard for no reason at all. Oh man, this is so annoying. I hate this. What the? No, stop. Do I really have to erase one by one? It's really annoying. And while I'm doing this, yeah, I just wanted to show you the, I guess, not a proof, but I guess a cool little, okay, sorry about that. Anywho, to go back to the original problem. So with this matrix, why is this a better basis? Well, so if these two are essentially creating the same lattice, let's repeat the problem. And let's say I need to find a point that is approximately 11.6, 4.2. Well, I know 11.6 is close to 12, and I know 4.2 is close to 4. So If I do it this way now, well, my answer is easy now. My vector is just 4, 2. Right? This makes sense. This makes sense, right? 4 times 3 is 12, 2 times 2 is 4. So now, if I use this vector, use a different color, one last color here. So I take, oh no, not that color, that was an ugly color. So now if I take my original matrix, or if I take my, um, so now if I do this, now if I actually work this out, you can see I land on 12, 4 with this lattice. I land right here. And you can see this is a much better distance. In other words, the whole point of this problem is that certain bases are better for cryptographic algorithms in this sense, for closed vector. Certain algorithms are better, and the way that this works in the cryptography, this is not how it's applied, but this is a very cool concept, a little box here, is that the good basis, I'm going to call it a good basis, is hidden. The bad basis is public. This is the whole point, because with a bad basis that's public, it doesn't matter who sees it because they won't be able to reduce to this matrix here in an easy fashion, right? Maybe in this example, it's pretty easy to find this unimodular matrix and find that these two are identical, but for hundreds of numbers, this is very hard. This takes a lot of computing power. This is why it's an NP-hard problem, right? So essentially, if you wanted to send me a secret, or if I was two people wanted to send a secret, you would encode an integer pair, like I don't know, you can just choose any, you choose an integer pair, multiply it by the public basis, the public bad basis, and then you would essentially keep tweaking it on the other side, such that the good basis, and then you would tweak it to find. So what essentially is happening here is you would encode secret message as integer pair, right? So this is the first step. Second step would be times this by bad basis, and then 3 would be optimize for good basis. Essentially, you want the other person to be able to find it, to be and to decipher it easily. That's the whole point of optimizing for good basis. So that's what we talked about yesterday. Basics of the problem. How they're all kind of written out here. Yeah, that was what we talked about yesterday. So today we're gonna shift our focus a little bit. This is a great review. Um, let's talk a little bit lattice reduction. How do we actually get here? And we have this. I believe this is lecture 2 in, oh, lecture 3 in lattices and cryptography. So we're kind of going to skip over this. Well, this is very complicated. It's very complicated stuff, but there's probably a reason. Yeah, there's probably a reason why. Nah, we're just gonna do it step by step. So we'll go and we'll talk about Graham-Schmidt orthogonalization. This shouldn't be too much harder. Okay. Graham-Schmidt orthogonalization. This is something that we covered in linear algebra. I want to see how they're gonna apply it, I guess, to yeah, I wonder how they're gonna apply it to a lattice. Okay, iterative process, right? This is an easy iterative process. Yep, I remember this. Yeah, orthogonal matrix times upward triangle. I remember doing this in linear algebra. This was a pain in the ass. I hated it. I hate doing this by hand is really annoying. Even by computer, you get actually you get a ton of error with the Gram-Schmidt. That's why I don't like it very much. I remember like a teacher, he really hated Gram-Schmidt, or he really hated this Gram-Schmidt orthogonalization just because you get a massive error towards the end. The thing is, in Gram-Schmidt orthogonalization, if you have one little error term at the start, by the time you compute to the end, that error becomes more and more and more magnified. So it's not a great way to orthogonalize things. So I'm kind of unsure why they bring it up here. I don't know. I mean, I'll write this down. I think I'll write this part B equals B U B is orthogonal, and then U is upper triangular. Yeah. Once again, I'm not sure why. I'm not sure why this is brought up again. I suppose we can do an actual review of the Gram-Schmidt orthogonalization process. I remember doing it. I remember annoying. I don't know that it was a very annoying process, so I hate having to review it again. We'll go ahead and review it again. So I'll just put like a little bracket and say like review guarantees orthonormal basis. I'm never doing this, but this is just my personal review. I remember this. I don't remember this though. This is new to me. Yeah, that's not a very. Sorry, I was looking at this. This is not a very good proof though. I don't like it very much. I don't. I think I'll watch this video. This is a good video. Watch video.
The Gram-Schmidt process. He knows a lot about all kinds of stuff. Professor Dave explains. Works. Let's examine the vectors v1 to vn, which serve as a basis for the vector space V. Our only requirement for these vectors is that they form a basis. We are no longer assuming any orthogonality between them. The Gram-Schmidt process takes these vectors and forms a new orthogonal set of basis vectors, which we will label u1 to un.
Save up to 45% on electricity for your home with the Jackson.
The process divide this.
Oh, yeah.
Then the third step
Oh,
will be to
gosh,
take the
yes.
vector v3 and subtract a similar term. The only difference is that now we take the inner product between v3 and u1 in the numerator. And we also subtract another term, which is the inner product between v3 and u2, divided by the length of u2 squared times u12's the any pi include no vectors of negative that times negative. Now taking u0 is how we compute. It ends up being negative
Yeah, the orthogonal basis.
1/2 times negative 1/2 plus.
Okay. I'll write this down because I'll have it in my notes. I think it's decent to have in the notes. It won't take too much. So we need to make, so just say essentially you take basis vectors, you need to form an orthogonal basis. And you do that by setting the first vector, you don't do anything, but then the second vector minus the dot product or the dot product, and then see, this is the annoying part is that on every iteration, you gotta compute so many more steps. It's kind of a because the thing is, you have to ensure that it's orthogonal to both. The problem with the Gram-Schmidt is you have to assume that it's going to be orthogonal to every single previous vector too. Every single previous vector. That's where it gets tricky because that's where, yeah. So this continue, and then what's the?
Two.
I want to see this.
All
That's looking pretty cool. Okay, I'm gonna write that. That's a good way to think about it. UI over UI times UI, yep, and then yeah.
the first
It's really annoying. Really, really, really annoying. And if you find an orthogonal basis, all you need to do is you just divide it. Ooh,
root 1/2. These are the orthonormal basis vectors we obtain from our
the basis vectors. Let's go back to the lecture. Okay, that's right. QR factorization. Yeah. All right, so let's consider for any lattice that is equal to, I don't know what that symbol is. I see it everywhere. What's all that? It's like a for loop. I'm not quite sure what this means. So let's have ChatGPT fully explain things that I might have missed. It looks like to me it's saying that the determinant L is. Oh yeah, it's right here. Uh-huh. Alright, alright. Right, we just talked about the volume of the parallelepiped. That was lecture 1. Go back to that. And here we go. Oh, it is. Tell the determinant of the lattice is the volume, or it's equal to the. Yeah, we know that det L. Oh, the volume. Oh no, that's right. The volume of the parallel. That's right. That's right. The volume of the parallel. The volume of the parallelepiped is the determinant of the lattice. That's right. Yeah, that's right. So how spread out or how dense it is. We talked about that recently. It says here, so he's all orthonormal. The product of the norms of normalized vectors is equivalent to the determinant of the lattice. Oh, that's right. I forgot about that. Is that here in the notes? We can talk about the determinants and its connection to Gram-Schmidt's. So look at that. Determinants and orthogonality. Because now I'm kind of curious. Determinant of the orthogonal matrix is plus minus 1. Yeah, but we already know that. Oh, it's pretty cool though. But I'll take the word for it. I'll just talk about this right now. So essentially, yeah, it looks like to me. So I guess we can just say that we'll say recall that determinant L is equal to the volume of PB. It's also equal to the determinant of B itself, or the basis vectors. Yeah. So in this case, this is just saying the product of the norms of the orthonormal vectors is the determinant of the lattice. Yeah, and then you can also think too now that matrix Let's look at the intuition. What does it say? Intuition. The determinant with lattice is visualized as the volume of the smallest building block. Oh, I see. So as I think less. Graham-Schmidt helps us compute. Okay, that's pretty cool. So it has to do with the parallelepiped, which is really interesting. Okay, so here's what we're gonna do, because this is a hard topic, and I don't want to really go on until I understand this. I don't want to go on until I understand this yet. So what I'm gonna do is let's try to find a video that I guess goes over what a parallelepiped is. So fundamental parallel. Here we go.
Grammarly now uses AI to help you write, not just revise. Type a prompt and generate a persuasive.
Hello everyone. In this video, I'm going to do an example related to dot product and cross product. The question or the examples asks to find the volume of the parallelepiped determined by three given vectors in R3. So the first one is the vector u221. Second one is a vector -4, 0, -2, and the third one is w 1, 0, -1. Okay, so let's see what does it mean. Questions like this. First, what is a parallelepiped? So if I have three vectors in R3, if they're good, meaning that they're not in a plane, then if this is U, this is V, I can generate a box which is of this form. The name of this solid object is called parallelepiped. Then the question is, what is the area, the volume inside this box? And we know that the
Okay, that's really cool. Let's like draw that out. I want to see how we drew that. That's like really cool.
of this form. The name of this solid object is called parallelepiped. Then the question is, what
Get
is
the
the area, the
geometric
volume
representation of it,
inside this box? And we know that the volume of that parallelepiped is given by this formula. First, you cross product two of the vectors, u cross v, or v cross w, or u cross w. Pick two of them, cross them, then you get a vector. Then dot product that vector to the third vector. So I use two of the vectors here, then the third component, third vector, I dot it to their cross product. Then I get a number. Here's a very important positive number, but this guy sometimes is not positive. We have to change it to a positive number by taking its absolute value. Okay, so pick two of the vectors, cross them, then the result, you dot that cross product to the third vector. Then you got a number, but you have to make it positive. You have to make sure that it's a positive, so we find its absolute value. So let's do this thing for this specific example. So let me first find U cross V. How do we do U cross V? So these are two vectors, cover the first component, then put the remaining components of the first one in the first row and the remainings in the second row of a matrix, then find its determinant. For the second component, you cover the second components, the remainings you put in the first column, first row, and the remaining put in the second row of a matrix. Find its determinant, then multiply by negative sign. This is very important. In the middle component, you have to multiply by negative. And for the third component, so you just cover the third component, put the remaining components of the first vector in the first row, the remaining components of the second vector in the second row of the matrix, and then find its determinant. What do we mean by determinant of 2 by 2 matrix? Let me write it here. Determinant of A, B, C, D is you multiply diagonal elements, A times D, subtract from that number the product of the off-diagonal terms. AD, diagonals, minus BC, off-diagonals. So then this means 2 times negative 2 minus 2 times negative 2 minus 0 times 1. I have a negative sign, so I put it outside bracket. 2 times 1, 2 are 2. So U2 is 2 to 4, 0. But this is on U cross V. Then the next step is find U cross V. It's a vector. It's actually here. Dot it to the third vector. In this case, is this. Okay, let me write these things down. I know that the cross product is negative 4, 0, 8, dotted to 1, 0, negative 1. What is dot product? Dot product, you multiply corresponding components and add them. In this case, it means I multiply this to that, negative 4 to 1, add it, multiply second component 0 times 0, multiply third components, and add them. Here I have negative 4 plus 0, negative 8. I get negative 12. Well, the second step is done. I did this, I did that. Then I got a number. I have to find its absolute value, meaning that if it is negative number, drop the negative sign. If it is positive number, leave it alone. So then we know that now volume of that parallelopiped is absolute value of U cross V dot W. And we know that that number is negative 12. Absolute value of negative 12 determined by these three given vectors. Again, be careful about each part of this thing. Cross product of two of the vectors, the results another vector. You dot product to the third vector, you get a number. That number is not volume. You have to find its absolute value, meaning that if it is negative number, you have to drop the negative sign, and if it is positive number, just leave it alone. That gives you the volume, and we did do this example, and the volume of this example, volume of parallel pipe in this example was 12.
This place is Calgary, Alberta.
Yeah, I mean, that's pretty. I guess it's worth doing an example. I'm kind of curious now. So I want to take it. Let's take another example. Let's do like a recall example. I want to test. I want to test to see how this works. So recall we talked about a special lattice formed by a good basis 3, 0, 0, 2. So column 1 is 3, 0, column 2 is 0, 2. So let's look at what the parallelepiped of these two basis vectors are. So essentially it just says that essentially we're just to find the parallelepiped is find the volume of u equals 3 comma 0 and v equals 0 comma 2. And you also need to recall that based on our last definition, this should just be equal to, wait a minute, was the Asian guy bullshitting us? Was he bullshitting us? Wait a minute. I think he was bullshitting us. Cofactor expansion of A3 matrix. I think you're bullshitting us. Which is a determinant for this. What a dumbass video. That was shitty. That was bad video. That was a bad video. I'm kind of upset. We're gonna look for a different video. That's annoying. MIT open coursework. Okay, you're at MIT.
I'd like to work on a problem with you, which is to compute the volume of a parallel.
Is it gonna be the same thing?
There's term, so I'm going to write plus. So for expansion on the first direction symbol, and then the 0, and I'll leave it at that.
Dude, it's the same thing. Okay, never mind. This is useless. So at least now I just know that parallelepiped is just the volume is just equal to the determinant. They're literally just equal to the determinant. So yeah, that's that. I won't do any more examples of that. Let's go on to this next theorem. Oh, I guess let's talk about this for a second. So lemma 2.1 just says the product of the norms of the orthonormal vectors is the determinant of the lattice. Oh, wait, that's easy. We can visualize this pretty easily. Look, let's visualize this. This is pretty cool. That's clear. Oh, I know there's a way to what? Is there a way to clear? I know there's a way to clear all, bro. It's not. I guess I just need to reload it. All right, there we go. Cool. So let's look at lemma 2.1 a little bit more in depth here. So if you recall, it says the determinant of the lattice is equal to the product of its orthonormal vectors, length of its orthonormal vectors. That's what I'm going to interpret these as. So, I guess let's consider an example in R3. So we have X, have Y, have Z. So let's just say we have these vectors. So let's create some orthogonal vectors here. Let's create a vector going that way, vector going this way. They're not exactly orthogonal. It's kind of hard to visualize R3 in an R2 environment. So what I'm going to do is I'm just going to go ahead and do an R2 example instead. That might be a little bit easier. So R2, this is pretty easy. We'll have, let's say, one vector going here. Let me just continue my plane. The other vector will go like this, right? So let's just say here are two vectors and say that you can even draw them out to, well, oh my gosh. There we go, to continue on to infinity and whatnot. So it's saying here, the product of these norms call R1, R2, the product of these norms, the determinant of the lattice. Right, so this is just common linear algebra. So we don't even need to make an example. This is just linear algebra. If the determinant of the matrix is the product of its orthogonal vectors, the same applies to this lattice. So essentially, the whole point of this is saying, once you've reached your orthonormal vectors, once you have that set, you can find the determinant really easily. So I guess it's a way to. So I guess that this does make sense. It's not trivial, but it does make sense when you think about it. Let's talk a little bit about 2.2, which states that 2.2 for any lattice. Okay, so that's kind of a long definition. It says you'll prove this later. So I guess it's more of just a fact, but it's just saying the body. So it's saying the parallelepiped of the basis vectors, or the parallelepiped of the orthonormal vectors. It's just the orthonormal vectors times the fundamental region. That doesn't seem that hard to understand because negative 1/2 to 1/2 n is the case for z to the n. That's the z to the n fundamental parallelepiped of a lattice space B. So that doesn't seem that bad actually, because this is I'll say this is an extension of 2.9. So this is cool. So that's probably an important fact to note. Lower bound. Oh, what does that stand for? Oh, that's the shortest vector. So it stands for any. So lemma 2.3 says for any lattice, the shortest vector of the lattice is bigger than the smallest. Oh, it's interesting. So I want to talk. Oh, this is a hard one to understand. There. Okay. So I'll set this for tomorrow. So tomorrow we'll just continue recapping what we learned so far. So we learned because we learned today geometrical interpretation of a parallelepiped. We extended 2.9 to include the body PB. Then we reintroduced Gram-Schmidt orthogonalization and talked about the benefits of being able to orthogonalize some basis vectors to construct a lattice in order to compute its determinant in much easier fashion. So we'll just review those tomorrow. I think tomorrow we'll spend some more time, and I also I want to look at this right here. So this lemma 2.3 looks really interesting. I want to look at this more in depth. I also really want to go in depth, get more understanding on probably. I want to get a more geometrical understanding of the determinant of a lattice. So tomorrow we'll finish up this lecture, and tomorrow plan we'll review what we covered today. We'll finish the rest of this lecture, or we'll probably get up like to 3.1 or so, and then we'll look at a video that covers this LLL algorithm in depth, and hopefully it's easier to understand. Hopefully. But yeah, it's a plan. Thanks y'all so much for sticking around. Another day, we're gonna chug through, but hopefully by the end of this week, we'll have both of these lectures done. So we'll be on track, and we'll get back to coding soon. I don't know. I mean, I think this stuff is really important to know first because this is the crux behind of why this is such a secure approach and why I should try to learn it. So, yeah, see you guys tomorrow.